Hello everyone. In the last class, we discussed about Mohr Coulomb failure criterion, and I mentioned to you that how this is modified in the tensile region in order to make this failure criterion applicable to rocks. Today we will learn few other things related to this failure criteria, such as its physical interpretation, and then we will learn about another failure criterion, which is a Coulomb-Navier failure criterion. So, in order to have the physical interpretation related to Mohr Coulomb failure criterion, we saw that this is the equation for the Mohr Coulomb failure criterion, and the failure will occur when this quantity tau f minus sigma tan of phi, this is equal to C. This means that the failure occurs when the applied shear stress less the frictional resistance which is associated with the normal stress on the failure plane becomes equal to the constant of the rock, which is C. Since it would not be reasonable to admit a frictional resistance in the presence of tensile normal stress, this equation loses its physical validity when the value of sigma, which is the normal stress on the plane of failure, goes into the tensile region. So, we saw in the previous class also that this equation will work fine as long as you have this normal stress sigma in the compressive region. The moment it goes to the tensile region or the moment its value becomes negative, this equation, which is tau f equal to C plus sigma tan phi, it loses its physical validity. The minimum principal stress, which is sigma 3, it may be tensile as long as this sigma remains compressive. This sigma is the normal stress on the failure plane. Take a look here in this figure that this Mohr circle is corresponding to uniaxial compression test. This corresponds to the indirect tensile test, which was Brazilian test, and this small one is for uniaxial tensile test. And here you can see that sigma 1 here for this small circle is 0 and sigma 3 becomes equal to minus sigma t. However, for the indirect tensile test, the major and minor principal stresses are 3 sigma t and sigma t. In case of the uniaxial compression test, the major principal stress is given by sigma c and the minor principal stress is going to be equal to 0. So, this Mohr Coulomb theory, it was retained by extrapolating the Mohr Coulomb line into the tensile region up to a point where sigma 3 becomes equal to uniaxial tensile strength. What does this mean? That we have this as Mohr Coulomb failure envelope. This was extrapolated in this direction in the tensile region, and then we put a cutoff here where this is sigma 3 value. So, this is how the Mohr Coulomb failure envelope was extrapolated in the tensile region. The minor principal stress, which is sigma 3, it can never be less than minus sigma t, and therefore, we need to respect this last constraint on the failure criterion, and in order to do this, we need to recognize a tension cutoff which is given by this line. And this cutoff is superimposed on the Mohr Coulomb criterion, and therefore what you get is this vertical line and then this failure envelope. Now it remains necessary to reduce the tensile strength and the shear strength intercept when we apply this simplified criterion in any practical situation. Why is it so? You can see here that this dotted line gives us the actual value of the criterion or the actual value of the strength characteristic. However, by extrapolating the Mohr Coulomb failure criterion, we have got this simplified version. Now, if you take a look, the shear strength characteristic by this simplified version will always be higher than the actual one, and therefore, when we use it for any practical situation, we need to reduce the tensile strength and the shear strength intercept, which is C. As in the case of soils, shear strength of the rock mass is defined in terms of peak and the residual stresses. You all know that the peak shear strength is the maximum shear stress which can be carried by the element. When I say element, this means that the element of the rock or soil. The next one is the residual shear strength, which is the shear stress when this rock element has undergone significant strain. This residual shear strength is always less than the peak shear strength. Take a look at this picture. Here on the y axis you have the shear stress and on x axis you have the shear displacement, and you can draw the stress displacement curve like this. So here wherever you get this maximum value, this is going to give you the peak value of the shear stress. However, here at the end when you have large value of the shear displacement here, corresponding to this value you have the residual shear strength which is represented as tau r. Look at this figure where the shear stress at failure has been plotted with the normal stress. So, you get two plots or two envelopes. One corresponds to the peak values, the next one corresponds to the residual value. So, you can see here that phi p is greater than phi r. This means that the frictional characteristic corresponding to the peak condition is more than the friction angle corresponding to the residual condition. Now, peak and residual angles, I mentioned that these are denoted by phi p and phi r respectively. In soils and rocks at the residual states where you have large strains, cohesive bonds are broken and therefore little or no cohesion contributes towards the shear strength. That is the reason that the cohesion at the residual condition is approximately equal to 0. So, you just extrapolate this failure envelope for the residual condition, just extrapolate it, which is shown by this dotted line, and you will see that it is intersecting at the origin O. This means that the cohesion intercept in the residual condition is equal to 0. That is, Cr will be approximately equal to 0 in the residual state. Rock mass, what happens to this at large strains? All the surface irregularities would be sheared off, and therefore this peak friction angle will be much larger than the residual friction angle, which is evident from this figure as well. So, the difference between peak and the residual friction angle is going to be significant, which will be approximately equal to the roughness angle I. This angle I is the result of surface irregularities or asperities in rock. When we discussed about the classification of the jointed rocks or the rock mass, we had some discussion about this angle I. So, this is the same as what we discussed earlier. The residual angle will be approximately equal to the basic friction angle of the rock material phi b. When I say rock material, means I am referring to the intact rock. As far as intact rocks are concerned, these are relatively impervious. We had the discussion on this aspect as well, that because of the absence of any kind of discontinuities in the intact rock, these are relatively impervious. However, in case of the rock mass, due to the presence of discontinuities, there is easy access to the water, because these discontinuities, they allow the water to flow through them. Now, what happens because of that? When the water is there within the joints, it exerts pore water pressure, and therefore Terzaghis effective stress theory becomes applicable to the rock mass in such situations. So, what this theory suggests, that is, the total stress is distributed between the rock and the pore water as effective stress sigma prime and u. That means whatever is distributed with rock, this is sigma prime, and the pore water pressure is u. And you all know that what is this effective stress theory? That is, the total stress is equal to effective stress plus the pore water pressure. So, this will be applicable to the rock mass. Now, once this is applicable, then we need to represent the Mohr Coulomb criterion to rock mass in terms of effective stresses. So, let us see that how this can be done. This is written as sigma 1 f prime, that is equal to sigma cm plus sigma 3f prime into tan square 45 plus phi prime by 2, or we can write it in this form as well, that 2c prime tan of 45 plus phi prime by 2 plus sigma 3f prime tan square 45 plus phi prime by 2, where this sigma 1 f prime and sigma 3 f prime, these are effective, major and minor principal stresses at the failure in rock mass. This sigma Cm, which is here, that is UCS of rock mass. C prime is effective cohesion of rock mass, and finally this phi prime is the effective friction angle of rock mass. So this is how Mohr Coulomb failure criterion for the rock mass in terms of effective stresses can be written. The question is how to determine the parameters C and phi in case of the effective stress condition for the rock mass. As far as C prime and phi prime for the intact rock is concerned, we can straightforward conduct the triaxial test and analyze the data of this test in order to get this C prime and phi prime for the intact rock. This is pretty straightforward. The question is how to determine these for the rock mass. So in order to do that, ideally what we should do is we should carry out the test on a very large rock mass, which includes the discontinuities as well. But to conduct such a test is very difficult, or it may not be really possible to conduct the triaxial under such ideal condition. So this is a difficult problem. The question is then how to determine this. The answer you will get maybe after few classes when I will discuss with you the Hook and Brown criteria. There we will see that how the parameters of Hook and Brown criterion can be used to determine the C prime and phi prime for the rock mass. So this was all about that I wanted to discuss with you as far as Mohr Coulomb failure criterion was concerned. Now to start with, now let us discuss the other failure criterion, which is the Coulomb-Navier failure criterion. This is more or less similar to the Mohr Coulomb failure criterion. However, the process of derivation of the model for this failure criterion is little bit different. So we will see the detailed derivation now. In this case, for the shear fracture to occur in the rock mass, the shear stress is responsible. So here this is a specimen where this is being subjected to the stress condition in such a manner that the major principal stress is sigma 1 and minor principal stress is sigma 3. There is a joint which is this one, which is subtending an angle of theta with the horizontal, and on this plane there is going to be a shear stress and the normal stress. This shear stress we are calling as tau, and the normal stress is sigma n. So we can write the force equilibrium equations in the direction parallel and perpendicular to the plane of failure, which is this plane. How? Let us see. So here we have that sigma n is acting. So say that this is point A, this is point B, and this point is C. So we will have sigma n into AC into 1, that is equal to sigma 1, and this sigma 1 is acting on this side, that is this one, which has AB. So that is going to be AB into 1, and it is acting in the vertical direction. So I need to find out the component of this in this sigma n direction, and because this angle is theta, this angle will also be equal to theta. So the component of this sigma 1 in this sigma n direction is going to be this force into cos of theta plus sigma 3 into BC into 1 into sine of theta. Why we are multiplying it by 1 is that the dimension in the plane perpendicular to the plane of this screen, that is being taken as 1. So from here I will be able to get this sigma n is equal to sigma 1 cos square theta plus sigma 3 sine square theta, because this AB and BC, they can be written in terms of AC. So from there you will get this expression. Then you can further simplify it. Sigma n will become sigma 1 plus cos of 2 theta upon 2 plus sigma 3 into 1 minus cos of 2 theta upon 2. And therefore from here what you will get is sigma n is equal to sigma 1 plus sigma 3 upon 2 plus sigma 1 minus sigma 3 upon 2 into cos of 2 theta. So this is the equation that we wrote, that is the force equilibrium equation, which was in the direction normal to the failure plane. Now similarly we can write the force equilibrium equation parallel to the plane of failure, which is this. So see here how I will write that. So that's going to be tau AC into 1, which is going to be sigma 1 AB into 1 into sine of theta minus sigma 3 BC into 1 cos of theta. So from here I will get tau is equal to sigma 1 sine theta cos theta minus sigma 3 sine theta cos theta, or tau can be written as sigma 1 minus sigma 3 upon 2 sine of 2 theta. Now what is the condition for failure? Which is tau is equal to C plus sigma n tan of phi. So just substitute the expression for tau and sigma prime in this expression. What we are going to get is sigma 1 minus sigma 3 upon 2 sine of 2 theta, that is equal to C plus sigma 1 plus sigma 3 upon 2 plus sigma 1 minus sigma 3 upon 2 cos of 2 theta, and this whole should be multiplied by tan of phi. Now say I represent this tan of phi with a quantity mu. So from here what I will be able to get is C is equal to sigma 1 minus sigma 3 upon 2 sine of 2 theta minus sigma 1 plus sigma 3 upon 2 plus sigma 1 minus sigma 3 upon 2 cos of 2 theta multiplied by mu. Now we have seen that the shear failure will occur when you have this tau minus sigma n tan phi equal to C. So the maximum value of this can be equal to the C. So when this maximum value will occur? So I take a mod of this quantity. So maximum of this quantity will occur when we have dc d theta equal to 0. So differentiate this C expression which we just now got with respect to theta and make that equal to 0. What we are going to get is this sigma 1 minus sigma 3 upon 2 into 2 cos 2 theta plus sigma 1 minus sigma 3 upon 2 into 2 sine of 2 theta into mu, that's going to be equal to 0. Now say I write tan of 2 theta equal to minus 1 upon mu. So if I write tan of 2 theta by this expression, then I can find out cos of 2 theta will be minus mu upon square root of 1 plus mu square. Simple trigonometry, and sine of 2 theta will be equal to 1 upon square root of 1 plus mu square. Substitute this here. So what we are going to get is C is equal to sigma 1 minus sigma 3 upon 2, 1 upon square root of 1 plus mu square minus sigma 1 plus sigma 3 upon 2 mu plus sigma 1 minus sigma 3 upon 2 mu upon square root of 1 plus mu square, and then you already have 1 mu here. So the C is going to be equal to sigma 1 minus sigma 3 upon 2 square root of 1 plus mu square minus sigma 1 plus sigma 3 upon 2 into mu. So see here that when we do this step, we get this equation, and if you just solve this equation, this is what that you are going to get. If you have 2 theta equal to minus 1 upon mu, we can find out cos 2 theta, sin 2 theta in terms of mu. Substitute these quantities in the earlier expression and you will be able to get this expression for C, and in the simplified version you will get this expression for C, or in other terms this also can be written as C is equal to sigma 1 upon 2 square root of 1 plus mu square minus mu minus sigma 3 upon 2 square root of 1 plus mu square plus mu. So, it is only that, there is nothing, no mathematics, nothing here, it is only that we are doing this jugglery of the terms on either side of the equality sign, or we can write it like this: sigma 1 equal to 2c upon square root of 1 plus mu square minus mu, plus sigma 3 into square root of 1 plus mu square plus mu divided by square root of 1 plus mu square minus mu. So, we can write different versions of these equations. Now, what happens under uniaxial compression? We will have sigma 3 equal to 0 and sigma 1 will give me sigma Ci, which is for the intact rock. So, just substitute these values here and what you will get is sigma 1 is equal to sigma Ci is equal to 2c upon square root of 1 plus mu square minus mu. What will happen for the tensile strength? In this case, you will have sigma 1 will be equal to 0 and sigma 3 will become equal to minus sigma t. So, again you substitute here in this equation and you will get here as minus 2c upon square root of 1 plus mu square plus mu. Now, just say that mu is equal to 1. So, for mu equal to 1, what we are going to get is sigma Ci upon sigma t, which is nothing but this expression 1 plus mu square plus mu divided by square root of 1 plus mu square minus mu, and if you just substitute this equal to 1, what you are going to get is 5.8. So, whatever are the equations that we derived just now, if you just take a look, what we are going to get is C is equal to sigma 1 upon 2 into 2c upon sigma Ci minus sigma 3 upon 2 into 2c upon sigma t, or we will get here as sigma 1 upon sigma Ci minus sigma 3 upon sigma t, that is going to be equal to 1. And this is what which has been plotted here in this figure, which is a plot between sigma 1 and sigma 3. On the sigma 1 axis, you have sigma Ci as the intercept and it is positive, and on the sigma 3 axis, you have sigma t as the intercept, which is with the negative sign. So, this is how the derivation of Coulomb-Navier failure criterion can be done. So, in today's class, we discussed about the physical interpretation of Moore-Coulomb failure criterion, and then we saw that how the expression for Coulomb-Navier failure criterion can be obtained. This is very much similar to the Moore-Coulomb failure criterion. However, during the derivation, little bit of difference is there. So, in the next class, we will learn about the concept of instantaneous C and phi. Thank you very much.